MRMAC, Mixed Reality Multi-User Asymmetric Collaboration.
Oh,
Do you have it? Does
you want
it
to
work out?
yes, wait.
Thanks for the intro. Hello, everyone. My name is Faisal Zaman. I'm from Computational Media Innovation Center at Victoria University of Wellington, New Zealand. And today I'm going to talk about MRMAC, the system we developed for multi-user asymmetric collaboration. Right now, we're all quite familiar with this kind of picture. This is how our typical remote collaboration looks like. We open up Zoom or Discord or any similar app, and we get a two-dimensional video stream of remote user. Where most of the camera have very limited field of view, so it constrains how much information can be presented. So although it works well for face-to-face conversation, like I'm actually presenting here on Zoom now, but it limits us to see other body language and gaze. Plus, our viewpoint is restricted based on the placement of the physical camera. So, for example, if I want to bring the audience into this conversation, I need to move the camera by myself, so which is not really interactive.
Sorry.
Okay, sorry. Plus, and there are more, especially when there's more people and large space, it's easier to get lost and feel very confused. Some interesting alternative out there, like 3D video conferencing by Google Project Starline, which uses high-res camera and depth sensor to create a 3D representation of yourself in real time, but it only track one face at a time, like for now, so it doesn't really scale yet. Then you have VR option, but the obvious downfall is you are totally actually disconnected from the real space. Then there are solutions like Microsoft Remote Assist, which combine the physical space with the augmented asset. But the remote user have very limited physical presence and interaction capability. And lastly, we have a mixed reality solution like Microsoft Mesh, which allows collaborators to come together in a shared virtual space. But what I'm interested in is how to bring this shared virtual space and turn it into a collaborative physical space, so that the local user can join with remote user to guide. And that brings me to, one of the immersive media like 360 video allow people to augment it into a VR environment and experience the remote environment as a first-person perspective. There's a lot of prior work has shown some promising result using 360 camera to induce various form of presence. However, and there's also like extensive work has been done to show that this capability for remote collaboration. However, there hasn't been a lot of work that addresses multi-user asymmetric collaboration, as the primary focus is mostly on one-to-one and one-to-many collaboration. And also, there's a lack of audiovisual synchronization, especially for multi-user collaboration, the data size increase, and it also affects the overall latency, and which also affect the communication and collaboration. So that brings me to our contribution, which we present a system that allows multiple remote user in VR to virtually teleport into a real world taxi space to collaborate with the local user in air. So we presented a design concept for multi-user asymmetric collaboration. Our research prototype were able to live stream 4K 360 video of the local user physical space. It supports face-to-face collaboration with synchronous audio-visual cues and multiple avatar and viewpoint sharing. We also have done some system evaluation with the focus of scalability and latency, as well as we have done a user study. In this study, we compared our system MRMAC against two baseline conditions. So here's our system architecture. We mounted a 360 camera at the local user space. And then we take the camera, we also take the camera feed from air user headset, and then the remote user actually receive those video feed and also send the viewport stream to the local user. We use a WebRTC SFU architecture, and our system was implemented on top of a Unity 3D game engine. So our system provides various type of communication and awareness queue. So for example, viewpoint sharing. So as I mentioned, we take the video stream from air user headset, which allows the user to see the egocentric view of the other user. The implementation and evaluation details of that system can be found in the following paper, which we have presented in the VRST last week. We also provide the multiple avatar. Since we're using single 360 camera, and the avatar is originally at the center of the camera, so we create it creates an overlap between the avatars. So we use offset compensation to slightly move the avatar around from the original location. This offset compensation also carried away while user interact or point to something. So for example, the tip of the pointer is still the original point, but the base shift along with the avatar hands. We also have personalized avatar. So we ask the user to take picture before they study, and then we use Ready Player Me and the headset plugin from the character creator with a Python wrapper to make the whole system automated. We didn't let them to customize it because of the time constraint. Finally, we also had a special audio. So, and apart from the communication cues, we also had a couple of interaction cues. For example, they can point to any object in the video, and they can also annotate. So let's evaluate our system. So we have checked our system for the latency. For the end-to-end latency, we broke down our system component by VR and air for VR and air user. And it was hard to get less than 400 milliseconds due to the inherent latency generated from the capturing device and other server setting. We also looked for the scalability. So we simulated 15 air user and 15 VR user to see how much we can push the system. So we up to 15, we got like less than 1 second latency. With the reasonable frame rate, and the rendering time was 60 plus FPS. As I mentioned, we also ran a user study. We got like total 36 participants. It was kind of uneven between the condition because we ran the study at the tail end of the pandemic, so it was very hard to get like a lot of participants. We had a 3x2 mix factorial design with 3 conditions. So for this study, we actually had a collaborative problem-solving task. For example, the VR user can see the virtual replica of what kind of model need to be built, and the air user the local user have the access to the physical Lego model. So the local user doesn't know what to build, but VR user help them to guide to build. As I mentioned, we had like 3 conditions. So the condition were the first condition is similar to Zoom. Where they used like 2D video camera. The second condition was passive 360 view, like traditional 360 video conferencing. And the final one was our system, MRMAC. Now let's talk about the result. So I know it's very confusing, so I'm gonna just remove the C1, C2, C3 and just call them Zoom 360 and MRMAC. I have nothing against Zoom, but I'm just gonna do that for the sake of the simplicity. So we assume that when user using our system, the spatial presence, which is the sense of being in the remote environment, will be higher. And from the graph, we see our system was quite significantly higher than the other 2 conditions, so it was accepted. And we assume because of the high quality 4K resolution video, they are able to see the environment, which make them feel especially presence. We also looked into social presence, especially the co-presence, which is the sense of being in the remote space with someone. So we thought it would be higher. And here is the result, which was significantly higher. So we thought, yep, except that one. And then we also assume that when you are using MRMAC, you would be able to solve the task faster. So we kind of see that the task completion time was like relatively low compared to other conditions, but it wasn't actually significantly lower. So partially accepted. And then finally, we also look for workload, which it actually tells us how frustrated they were or how much like mental load they had. So we see for MRMAC, they were able to solve the task relatively easier than the other condition. And we also check for the systemic usability, which is way above the the baseline 68 score. And finally, for preference, we ask people which system you prefer from various form of presence. There was a tendency to prefer our system. And from their feedback, we found that people felt in MRMAC was more engaging, and they had more rich conversation when than they would be in the 2D video conferencing or conventional 3D video conferencing. So we ran all the thing in the, so we actually didn't incorporate the depth information. So in the future, we're planning to add the depth, real-time depth reconstruction, so they can also walk around in this space. And our system was evaluated in the local network, so we would be, it would be interesting to see how it performed in the very challenging environment. So more in-depth user study can be conducted in the future. So to wrap things up, what we've done here, we presented a fully bidirectional asymmetric collaboration system. So our system supports real-time communication, audio-visual synchronization, and at the same time, it seamlessly blends the virtual asset into the scene. We have also done the user evaluation, which shows the reasonable scalability and low latency performance. We have also run a user study where participants were able to collaborate and solve the tasks faster. And the overall, the participants shown that the preference on our system was overall higher than the other system. And thanks to all of these people who helped in many ways. And thanks for listening.
A great talk, Faisal. Next up is Mr. Smith, who will be talking about how visualizing emotions affect interpersonal trust and task collaboration in a shared virtual space.